Welcome back, chemistry fans. Today we are going to finish up Unit 4 with Topic 4, where we are going to talk about net ionic equations. Going to warn you that this is a complex topic. It is not difficult, but it does require some prior knowledge of how to balance a chemical reaction, how to predict the products, also how to predict the formulas. We're going to have some knowledge based on some of our previous work with nomenclature. All right, let's jump into it and see what we can figure out together. Okay, so a net ionic equation. The word net does not mean that we are using some kind of a fishing mechanism to gather information. What it's talking about is the overall. That's what the net means. It's the after we have discounted what is not necessary, made all of our expenditures, what is left over. That's what we're going to talk about. So we're going to have a couple of pieces that we have to deal with before we can get to a final simplified version of a chemical reaction. Okay, so one of the things that I liken this to are things that are no longer necessary. And so if you were to look through this list of things that are no longer necessary that may have been in your lifetime, but certainly in my lifetime, we could talk about CDs easily. We could talk about VHS tapes. You could talk about landlines. You don't have any need for that one. The Postal Service is going away quite readily. A DVD player, oh my goodness, we don't have those around our houses very much anymore. Film, not even knowing how to work with one of those things. We got rid of what was not necessary. We had newer products that came in, and now they're just not necessary anymore. And that's what we're going to try and work our way through with chemistry. We're going to get rid of some of the materials that seem like they're repeating or they didn't actually participate in the reaction. So what you will notice in this one highlighted are materials that are the same on both sides. So what you see in here is that there is a sodium ion on the left, there is a sodium ion on the right. Well, if it did not change, then there really is not a need to write it down because it didn't actually participate. It may have temporarily bonded with someone new, but then it went right back to where it originally was. So they are going to eliminate any materials that happen to be the same on both sides of this equation. And so what you're left with are the materials that actually do participate in reaction and change their states of matter, change their partners. So one of the terms you're going to hear me use is dissociation. And all that means is that you are going to take an ionic compound. Ionic means it has a metal and a nonmetal, and it's going to break apart into its constituent pieces, into the metal and into the nonmetal. And then what's going to happen is that this can only occur while it's in water. So we are going to say that these particles are going to get surrounded by water particles, and that's going to keep them separate and not allow them to continue to come back together. So this salt crystal is breaking apart into a sodium ion here and a chlorine ion down here, and they're being separated because they're being surrounded, peer pressured, hot boxed with a group of water molecules around them. So they don't just do this because they want to be mean. There is attractive forces. The sodium has a positive charge. Well, there is a polar nature to the shape of this water molecule, which allows it to have a negative side of the particle, which surrounds the positive sodium. Likewise, the water molecules have a positive side with the hydrogens that are then attracted to the negative on the chlorine, and it prevents then the sodium and chlorine from getting back together. So they dissociate from one another. Another term that you'll hear me talk about are spectator ions. So spectator ions are these dissociated particles which do not change. So yes, we may have silver and nitrate together on the left, and then on the right, we have it together with sodium and nitrate on the right side. What this means, though, is that the nitrate, the NO3, it never actually changed its formats, because when it was on the left, it dissociated into two different ions. When it's on the right, it may separate again and get itself back with the sodium or with the silver. And so it never really changed its state of matter. It stayed as an aqueous ion that is dissociated. Therefore, it's a spectator ion that can be eliminated from the reaction. All right, so here's the process. In this reaction, what we want to focus on is being able to put the state of matter labels. And you're saying, well, how do I know what the state of matter is? There's going to have to be context clues. If it is an ionic compound, we are going to have to assume that it is going to be in water. It will become aqueous. If it's an element by itself, well, then we have a little bit of knowledge that chromium is in the middle. It's a solid. It's not going to be an aqueous ion because it can't exist by itself. So that's not how it's going to be written at the start. Now, we may turn it into an ion later, but for right now, it's a solid, the same with nickel on the right. So we need to be able to establish what the states of matters are. Once we do that, we then need to split up these aqueous ionic compounds into their individual ions, into the nickel and the chlorides. And then we need to be able to represent them with the number of ions. So notice up here, I have 3 of the nickels. I would have a total of 6, 3 times 2 for the chlorine. So in the next step, we need to represent that. We need to state that there will be 3 nickels and 6 chlorine ions, the same as as what's happening then on the product side. Now, notice though, you're starting to see some similarities. The chlorine did not change. So therefore, we are going to ultimately be able to get rid of those chlorines from the equation. And so that's what happens here. We are left over with the materials that actually change their state of matter or form new compounds, which have different states. If they stay aqueous on both sides, we can eliminate them. So net ionic equation has 3 different steps. The first step is the molecular equation, which we practiced whenever we were balancing the reactions and predicting products. It has listed with it the states of matter. Then the complete ionic just takes that molecular equation and it splits it up into individual ions, to which you're saying, well, how am I supposed to know when it becomes an ion? Because it's in aqueous state. If it's in an aqueous state, it will separate. If it is in a solid or a liquid or a gas, it does not separate. It stays together. So the aqueous is going to split apart into its individual ions. You say, well, how do I know if it's an ion? Because we've practiced our polyatomics, we've practiced our charges whenever we were creating formulas. So now in this second step, I have all of the ions listed out. The final step is the net ionic equation, where we cancel out anything that is identical on both sides. If I notice that there is a material that is the same on both sides, it gets eliminated. If I don't see it the same on both sides, it must stay in as part of your net ionic equation. So here's some more examples. In this, I had originally sodium hydroxide and copper chloride. And what it is a double replacement, so it would have gone to sodium chloride and copper hydroxide. Now, the copper hydroxide is going to actually be a solid. So it stays, but all of the other materials, they would have been aqueous. So that's why the sodiums get canceled. That's why the chlorines get canceled, but everything else gets to stay. Now here it is. Again, I have sodium chloride. It's going to get split. I have a silver nitrate going to get split. But on the right side, notice the silver chloride is a solid, so it cannot get split up. It stays the same. Whenever I split this up, it gets dissociated into its ions. The sodiums are going to cancel. So are the nitrates. And what I'm left with is just the material that actually participates in the reaction. Notice the states of matter for the silver is different. It went from aqueous to solid. The chlorine went from aqueous to solid, so it gets to stay. So in the next example here, I have a molecular equation that has soluble, it has aqueous silver nitrate going to split up. It has sodium sulfide, which is going to be aqueous split up. Now the products over here, this is a solid and this is an aqueous material. Because it is aqueous, it does get split up, but because this is solid, it stays the same. Now in the ionic equation, the silver has changed, so it gets to stay. The nitrate, however, did not change. It's going away. The sodiums did not change. They are going away. So what I'm left with is just a silver and a sulfur that changed into a silver sulfide solid. So let's try a couple of examples for ourselves, and then we'll call it a day. Silver nitrate and lithium bromide, both of which are aqueous. It's a double replacement reaction, so they are going to switch partners, AgBr and lithium nitrates. All nitrates are soluble. The silvers are generally not, but except for this case, it's over here with a nitrate, so it was soluble. So this one is going to be solid. So I'm now going to write my split this up into its ions. So I've got silver and nitrate. I have lithium and bromine, both of which are aqueous. Then on the right, I've got silver bromide, solid, and I have lithium aqueous, and I have nitrate aqueous. So I look at this and I say, well, what is the same on both sides? It is this nitrate, and the lithiums did not change, but everything else did. So therefore, my final answer will be Ag plus 1 aqueous plus bromine aqueous produces silver bromide as a solid. That's my net ionic equation. I'm going to do one more, and then we're going to call it a day. Chlorine gas. Chlorine is a gas, it tells us. It is diatomic. It's bubbled into a solution of potassium iodide. Potassium iodide, assume, is aqueous. What it's going to produce, this is a single replacement reaction. So the non-metals are actually going to be the ones that switch. So I'm going to have KCl, which is aqueous, and I'm going to have iodine, which actually forms a liquid. Diatomic, though. So I'm going to balance this with a 2 here and with a 2 here. You can't see that 2. Now, because my potassiums are going to split into aqueous, I am actually going to be able to cancel out potassiums because they're both aqueous. But everything else is going to stay. So I'm going to have as my final answer, chlorine gas plus 2 iodines that are aqueous produces 2 chlorines, which are aqueous, and iodine, which is a liquid. Okay, this only gets difficult if you don't practice this. You must engage with the content. You must practice for the test that's going to happen next class. Thank you so much for staying with me. I will talk with you again soon. Farewell. Bye-bye.